on this computer?
11 people in class, including the 3 of us right now.
Okay, so that's like on,
Not including.
yeah. You know your project's not due until I grade them, and I have to grade the 380 exams first. So where I was at basically here, before I was so rudely interrupted by my lack of technology, we're programming this row, and we're trying to program this cell right here. The other adjacent transistors are going to get high voltages on their whatchamacallit too, and on their gate. So they actually have some tunneling going through, some parasitic tunneling, and this might be enough to change one of these that are up on this part of the distribution from a 1 to a 0. So I may get some errors, and this is called program disturb, is the error name as they call it in the Flash world. Yeah, see, program disturbed. All cells in the same page on that same word line string get the same gate voltage. Now there's another thing called pass disturb, because the other cells in the string right here get higher gate voltages. Now one thing that they do as they're programming, they have a program, this is part of the reason why it's so slow to write to Flash, is they have a program and verify algorithm. What they're going to do here is they're going to program this cell for a very small amount of time. And then they measure it and see if it's within specifications for it being a 0 or a 1. If it's not there yet, they program it for a little bit longer. And they have to keep on going back through this loop until they finally program the correct voltage that they want. It minimizes the amount of time that you're programming the devices, and it verifies that you actually wrote.
So it's slow writing, but it makes sure that it does actually write.
Right, yeah, and we're using this algorithm in the lab for other things.
So what is the extent of program disturbance? Does it just like basically prevent like things from being written properly, or
no,
actually damage the circuit?
No, it doesn't damage the circuits. It's going to give you errors. The program disturb, what's going to happen here is, okay, let's say this was a 1 and this was a 1. And suddenly, even though you're programming this to be a 0, you've put enough electrons through these 2 gates that they become a 0, even though you didn't mean to program them to be zeros. You can, if you go back and erase the whole block, you can get them back where you want them to be, but you may have errors in there. So what they do is they use error correcting codes, store extra data that verifies the value of these bits, kind of like Hammond codes and things like that. So 64 bits, I probably have another 64-bit string that just verifies the correctness of that 64-bit string. And I lose roughly half of my memory.
Accept the risk. that was intimidating.
They're all like that. Okay, so basically this program disturb is going to give me errors in my readout. So I need to store data in extra bits and something like Hammond codes to actually be able to verify I got the right data.
And so if say the verify algorithm doesn't work per se, like this is just a circuit.
Right.
Like if it say the verify algorithm doesn't work and a program disturb occurs and it writes everything to zeros, does that basically mean it doesn't write correctly? And
yeah, you may be able to go if you overwrite the cell that you're trying to write to, then you could go. Well, you can't. You got to erase the whole thing.
Okay, so is that basically like?
It would just take more time.
Okay.
Okay, but generally the program and verify works fairly well, but you may be programming more cells than you intend to program.
And then you take up more space.
And you take up more space.
And that's not good.
Right. So this is okay, before I actually program any cells, in order, because what's going to happen is if I have something programmed to a 0, and it through program disturbs, over time, the mean of this is going to keep shifting this way because I keep adding electrons to it. So before I rewrite data to any block, any page, any block, what I'm going to do is erase the whole block. And I erase it and I drive all those electrons out of the floating gate and make the threshold even lower than my 1 value. So I drive the everything down here, and then I program, this is a 4-bit cell, so then I program that one to 1, 1, and I program the cell, this is a multi-level cell, I program them where I want to go. And this helps clear out some of that built-up charge from the program disturbs. So this is why I have to erase an entire block at a time. I have no choice. Does that make sense?
I mean, if we can program a 0, it's just not something that's ever actually used. Is that you erase the entire thing and then reprogram it all back?
Yes.
Okay.
You erase the whole thing and you erase them below that level. So then you've got some program and verify headroom here. Instead of just saying whatever random value they erase to, I have to add a little extra charge to get them to their lowest lowest threshold state.
And if we somehow speed up that process, then we'll have our universal memory.
Not with Flash. Flash is going to be DOA in probably about at least 5 years.
Is it really?
Yeah. We'll have brand new, we'll have to replace our SSDs with something more modern.
Super re-RAM.
I'm okay with that.
Yeah. Yeah, super re-RAM. I like that name. So remember, okay, a row, one entire row, one entire word line across the entire array gives me a page. A block is all the word lines in a string. All the pages, all the word lines, so all the pages in a string. So that's 64 times, 64 pages per block. Wow. And a NAND is just a randomly selected 8192 blocks. Okay, where are we at?
SSDs, but they don't run on SATA connections. They're more direct to the processor stuff.
Okay, so that one's kind of pointless. This is just another, it's a floor plan. I've got a memory array. I've got a row decoder. I've got sense amps. It looks amazingly, and peripheral circuits looks amazingly like a DRAM. We went through the details there. So the pinout. Now this is a TSOP package. We know there's more modern packaging tech options, and we'll look at some of those in a minute. But basically the ones we need here, these are all the control signals we need. And yet there's not many of these. So I've got 8, 9, 10, 11, 12, 13, 14, 15 pins. Why do I put it in a 48-pin package? There you go. A lot of VDDs and grounds to lower the impedance between the VDDs and grounds. And we know that even this TSOP is getting obsolete. We'll look at some more options in a second. This is a beautiful thing, and this is something that you guys should start thinking about as engineers. Okay, I've got a 2 GB memory. Now, I've got somebody who's already went out and built 5 gazillion printed circuit boards to hold this 2 GB memory chip. And suddenly they realize that for their design, they need to add some more memory. 2 GB isn't cutting it anymore. They need 4 GB.
So then they have to redesign the 5 gazillion.
So they don't have to redesign the 5 gazillion printed circuit boards or spend a lot of engineering development time in getting a new board out. So this chip, you get the same footprint, the same basic package Whether you're using 2 GB or 4 GB, all you have to do is there's a couple of more lines you have to drive.
What's with the like little slash? That I'm confused by that.
Oh, I don't know.
Is just
No, they don't cut the chip in half.
yeah, that's what I'm confused about. I was like
Okay.
why is this that necessary?
Right. And you can see like through here, like on the X8, there's just a lot of the pins are similar. To the X16, you may only have to rewire a few wires, and then people can go instantly upgrade without having a whole bunch of development time. Oh, I hate this part. It's programming. Skip it.
Yeah,
Well, it's important in the sense that, you know, just like microprocessors, anything, there is a basic assembly language associated with Flash. There's a basic assembly language associated with with DRAM chips. You have to be able to, if you can program in that. So if I have a command, what I'm going to do is I make command latch enable high, and whatever's on DQ7 through 0 becomes my code. If I want to put an address in, then I make address latch enable true, and whatever is on my data lines becomes an address.
so sometimes
Don't do that. If I want to write data in, then I put the data, I put the command phase data in is in there. I make write enable true, and what's on the data bus becomes actual data. If I want to read, I make read enable true, and what's on the data bus becomes my data out. That's all this is basically saying. For any operation, I've got to get this all right. I got to stroke the right signals, make sure command and address latch enable aren't true at the same time, and write enable and all that stuff. And I can multiplex the data pins that way, have fewer pins. Now, if I want to read, I have to put a command latch enable in, put the command for read on the data bus, then wait, then put the address latch enable true, and put the column address first, keep the address latch enable true for another cycle, put the row address in, and then put the command in and read. That probably means read data cycle. The chip comes back and says, oh, I'm busy now because I'm out processing your command. And then once that comes up, your data is on the output bus.
Huh.
And every single memory chip, it's like learning how to write to a new microprocessor. You can buy as intellectual property memory drivers and things like that if you don't know how to do it yourself. If you have something like a Cyclone 5 board like you use in 310, the basic memory drivers are already written for you, so you don't have to go through this process and learn the whole chip.
Hey, you mentioned 310.
Yeah, because I found something more interesting to do. This happened, you know, this has really happened to me 3 or 4 times in my life. I decide that what I really want to do next is become an FPGA designer. I've had 2 job offers. Then that would be all I would have been done is an FPGA designer, and they knew I didn't know what I was doing. I was blatantly honest with them. And there's been like 2 or 3 other times when I took a class at USC in FPGA design. But what always happens to me before I actually decide that I actually sit down and start doing FPGA design is that this wonderful thing happens and I realize I don't have to do it anymore. I have a better opportunity.
Daniel Copeland said he got a FPGA design. No.
Yeah. I mean, it's good work and it's easy to find. It's easy to find jobs as an FPGA designer. It's just not something that excites me.
It's not fun.
So it's maybe fun for some people, but it's not something I like doing. Not everybody likes doing the things I like doing. which is
Physics.
physics. So the NAND flash is usually in flash cards, USB sticks, and solid state drives, where I'm getting out big blocks of data all at one time. And here's some more pretty pictures.
SD cards.
SD cards, yeah, and we all know what those look like. Again, in smaller and smaller cards, you know, this says 2 gigabytes. I've seen 1 terabyte in one of those. And the way they're going to get there is what the tricks I'm going to show you next, which is more exciting. This I like. Okay, this is a very typical thing for a company to do. Where does all the cost from this thing come from?
Look at my glasses on.
Okay, we're gonna think about, and we're gonna break down the cost of this. Then probably the number one cost in this whole system is engineering development. You've got to pay some engineer to put this whole thing together. Okay. The number 2 driving cost in this is parts, but the most expensive part is probably the flash. So the most cost-effective way to sell these things is, let's say this is a 2 gigabyte flash drive.
Yes.
I can also sell it as a 4 gigabyte flash drive. Same engineering design. All I have to do is put the extra flash chip on the back. Okay. So I save a lot of engineering development time.
That's the thing that you were talking about earlier.
Right.
With how the gazillion PCBs manufactured.
Yes.
Yeah.
So I just put that extra chip on there, and now suddenly I can sell it for a higher cost to the user. Because now he's got a 4 gigabyte flash drive, he's willing to pay an extra $5 for it, and I've probably only put another $2 chip in it. Motorola was amazingly
efficient.
No, okay. One of the things we did at Motorola, the development costs were so high, we really only had one phone. Everybody got the same phone. The person who paid for the high-end phone, we turned on a couple of extra bits in their thing that enabled some high-end features.
Oh, so
it's exact same phone, but we disabled the software in the lower end phones.
It's literally like how they do Teslas nowadays.
Yes, they just
like how ludicrous speed and self-driving is something that's already installed. It just has to be turned on.
Right, and they charge you to turn it on.
Yeah. So what ludicrous speed actually entails.
Okay.
For Teslas.
I'm over it. Okay, so here's a block diagram for an SSD. I have a whole bunch of flash chips in there. These are raw NAND. They don't have controllers in it because they're a lot smaller and a lot cheaper than flash with their individual controllers. And we don't want the flash controllers competing with each other. We want one controller to rule them all.
And not throw it in the volcano.
Yes, okay. We have some passive devices in there, you know, like capacitors, inductors, and the not so passive devices like voltage regulators and things like that. And we've got some kind of interface into the host computer, some kind of like PCI interface or something like that. So that's how we're going to put the whole thing together. Another thing they found, and this is kind of an upgrade, is if I put some DRAM in there, what I can do is use the DRAM as a buffer. So I get all the data that I'm expecting to be asked for next off of all the flash at once, store it in DRAM, and then I can have higher read and write access speeds because I'm actually reading and writing directly to the DRAM and then buffering that off to the flash as I need to. And we'll look at a little niche application for MRAM. That will be your pre-lecture assignment for emerging memories. And it has to do with SSDs and this DRAM.
The 18.1?
Yeah, the 18.1. The next thing I have to do, if I put DRAM in here, DRAM is volatile, so I need some kind of battery backup. So I don't lose all that data that I've just written to the drive if I get a little power glitch. So there's some kind of super cap or battery backup that takes up space. Now you could take this whole thing right here. This is pre-lecture 18.1, and you could just take that whole thing and replace it with MRAM. And suddenly you have non-volatility, and you get rid of the battery. And the battery is expensive enough. It actually makes up for the cost of MRAM.
Yeah. Where's the fault?
I believe so. Yeah, it's
Okay.
kind of weird to think about.
Game Boy, yeah.
Yeah, Game Boy cartridges, they had a little internal battery that if it ever died, you lost all of your memory.
I remember those. Okay, so inside the SSD, I've got to have both the flash and the microcontroller and the interface to make sure that for my host, for my motherboard on my computer, that this looks like just something on a standard PCI bus or whatever bus it's on. So you do need brains inside an SSD. Memory control. Oh, I gotta go through all this stuff. I sound thrilled, don't I? Where's my endpoint?
Did we have a stop point? And we have to go through all of this.
Okay, so I'm gonna have to talk fast. So big things we've already talked about. The memory controller, the different tasks it has. It's got to do the host interface. It's got to do something called wear leveling and garbage collection and bad block management. It's got to do the error correcting codes to make sure that those cells that got disturbed are you have the real data and not the disturbed data. And I need the interface to the flash.
All those kind of part of the program verify.
Yeah, it's a program, and it's basically a little processor inside the SSD. It's like, I think at one time, last time I heard, somebody counted up how many hundreds of microprocessors there are in a single automobile. Okay, so block management. I've got this logical address. This is the address that the motherboard is asking for. And I've got a physical address. Which flash, which page did I actually map that to? I could map it to different places. Let's say I get the request for this data like this. This is what I want to write. These are the available addresses, so this is where it goes. Now this is like guys in a warehouse, a truck comes in, and they need to unload the truck. And they just take everything and just dump it in the first available place they can find.
First available shelf.
Okay. Yeah, and they keep on doing this. And then another truck comes in that's empty and wants to get filled up from the warehouse, and nobody knows where anything is. What block management does, he's the guy running around with a clipboard, writing down where these guys are throwing these boxes so he can, so that the guy with the empty truck can retrieve them later.
You could write a Disney movie off what you just described.
Three Stooges. Okay, so this is what block management is. It's making sure that you know what logical address is, what boxes are in what place, which physical address. Because I can dump them anywhere there's empty space. Okay, wear leveling. We want to minimize disturbs. There's another thing going on here with these single level cells. On the average, you get 100,000 program erase cycles before these things just die. If you go to the 2-level cells, the multi-level cells, you only get 10,000 program erase cycles. So ideally what you want to do in these flash is you don't want to write to block 1 every single time block 1's open, because you'll blow up block 1. You want to just randomly put it all over the chip and try to keep the same number of writes to each block. So this is part of the microcontroller's job.
Like guys coming into the warehouse, like, put it over there this time.
Wait, we used this place that we filled that place up last time, so now we got to put it over here.
And we remember like last class, didn't we, that single level cells are like generally better than?
They're higher performance. They last longer. They're more durable. higher performance, faster read and write cycles.
More space,
Yeah.
more cost.
Yeah, but they do take up more space and they do cost more. So garbage collection. What happens is every once in a while, one of the blocks goes bad because you've just written to it too many times, or it's a weak block or whatever. Oh no, this isn't garbage collection, never mind. Garbage. I'm throwing a whole new meaning to this term. Garbage collection is basically, I've got stuff that's stored like this, and I want to be able to read it out faster, and it'd be more efficient if that was stored like in one block. It's kind of like defragging your disk. So you're going to want to go through periodically and maybe take the entire movie and put it all in the same physical locations to make reading it out faster.
That's essentially what physically happened with EFRAG.
Yeah, you just move stuff around, and then you get big gaps where you have empty space, and then those big
It's like,
gaps are easier to.
Learn to pack things better.
Yes.
Far after going to Sam's.
Yeah, it's like repacking your car when you've been to Sam's Club. That is a perfect analogy. You may have to do it, and then you go to Price Club afterwards, and you may have to repack it all again to make it all fit in the right place. Okay. So bad block management, what happens with time? Some of these don't last 100,000 cycles or 10,000 cycles. Some of them go bad. And some of them are bad when you first power up the chip. So you want to be able to have like those redundant rows and columns in DRAM. You want to be able to map out the bad addresses and don't write to them. Okay. Error correcting codes. Oh, you get to do this on homework 5.
No, we haven't even done homework 4 yet.
Some people have.
Some people.
Yes, Bryce has. Sometimes you read the incorrect data because something's been disturbed or there's noise, read disturbs, program disturbs, things like that, leakage currents. You add extra bits on the end of your data. They're kind of like parity bits to encode the data. And it's a special kind of parity bits that can detect and correct errors. I think if you have like 4 bits, you can correct for like 2 or 3 errors in a big string. If you have twice the number of data, you can pretty much correct for everything. We'll do some calculations with Hammond codes on homework 5. Aren't you excited?
Hammond codes in Kimbo.
Yes. The most simple example I can give is like an even parity. All this tells you is that if one bit's wrong, you know it's wrong. You can't fix it though. You can't tell which one is in there. Hammond codes, you can actually fix the bad data. Oh, good. This is what I was hoping to get through. Okay. So what do we got here? If I have one memory, I can get less megabytes per second than if I try to read from 4 memories at the same time.
Makes sense.
Yes. So if I read from 4 memories in parallel, I can get a higher data throughput. It's not that I get 4 times as much data. I don't get 4 times the data rate with 4 memories, and I'm frozen.
Yay.
Okay, I'll be back in a minute. But if I have 4 memories, I don't get 4 times the data rate because I've got overhead of managing the reading and the writing from the 4 different memory cells. I will be back. I'm on slide 35.
You got 15 minutes left.